Hello everyone and welcome back to another video. I hope you had a very food-filled Thanksgiving, whether that was composed of turkey or steak or duck or something or the other. Food-filled. But what I want to consider in this video is, at least in theory, simpler than a lot of the recipes my mom and I tried to make. So say I'm here on Earth, right, and I have a ball. And I'm bored, so I decide to drop the ball. What happens? Well, from my reference frame, what's going to happen is the ball is just going to fall, right? It's just going to go down to the ground. But say we have Tom Petty over here, all the way on the right in his little rocket ship, and he's accelerating. And he's accelerating such that the ball is not accelerating in his reference frame. So from his point of view, the ball, in fact, is not accelerating at all. It's just also moving at a constant velocity. So to draw this out, we have two quote-unquote arguments, you might say. From my point of view, what's happening to the ball, so say this is time right here, so time, and this is the height of the ball. So from my point of view, that's what's happening to the ball. But from Tom's point of view, what's happening is not that. In fact, from his point of view, from his reference frame, the position of the ball might look something like this. So we have two competing arguments here. We have mine, that says, well, the ball is moving in a parabolic path, but then we also have Tom's, who is saying the ball is not free falling at all. It's, in fact, just staying where it is. So which one is right? And the answer is both. It just depends on perspective. So let's quantify this slightly more. So in Tom's reference frame, the acceleration of the ball is just going to be zero. So to write that out, we have the second derivative with respect to proper time of every component of his coordinates, so every alpha component of his coordinates. We're going to have multiple x's here, so just to clarify, his are going to have these little bars on top because it's hard to differentiate between a capital and lowercase x. But from Tom's point of view, the acceleration of the ball right here, every component, it's just going to be zero. It's not accelerating. But for mine, well, it's not zero. So what can we take away from this difference? Well, let's expand Tom's equation right here. So we can expand this as the derivative with respect to proper time of the derivative with respect to proper time of each component here of Tom's position is going to be equal to zero. But we can use a coordinate transformation and transfer this to my reference frame, and this will still equal zero. So to convert from one coordinate system to another, we can just use the multivariable chain rule, which states the following, that the derivative of, say, x right here over d tau is going to be equal to, well, the partial derivative. So the partial derivative of Tom's coordinates right here with respect to my coordinates, but then or every component to my coordinates, I should say, and then times the derivative of every component of my coordinates, and then divided by, or not divided by, or the derivative of my coordinates with respect to proper time. And here we will be employing the Einstein summation convention because it would be a lot to write multiple sums. So right here, since the mu is repeated, there will be an implied sum over mu. So based off of that, what do we have? Well, this right here, the derivative on the outside just doesn't change. It will in a second once we, apply it. But right now, we just have this right here, according to our multivariable chain rule. We just have partial Tom's coordinates with respect to my coordinates. And then we have the derivative of my coordinates with respect to proper time. So we can use the product rule, right? So first we can differentiate this term right here. So our first term is just going to be partial Tom's coordinates, or pardon me, every coordinate of Tom's coordinates, so partial x alpha, and then with respect to my coordinates, so partial x mu, and then times the derivative of this right here, so dx mu, or d squared x mu, and then divided by dt squared. And I may say divided by dt squared. This isn't actually a division, it's a second derivative. So I suppose what I should have said is the second derivative with respect to proper time of x mu. And then, by the product rule, we have the second half right here. We have dx mu, d tau, it's a mouthful. And then we have times the derivative with respect to proper time of this right here. So we have partial x, which is, Tom's coordinates, so partial x alpha, and then divided by partial x mu. And the question becomes, how do we evaluate this? Well, this right here is just going to be another application of our chain rule. So this term on the outside of the derivative is just not going to change. We just have dx mu over d tau. And then by the chain rule, what we're going to have is the second derivative of Tom's coordinates, so partial x alpha, and then with respect to x mu, and then with respect to x nu, because whenever we take the chain rule, by our multivariable chain rule up here, we're going to have another index we're going to sum over. So based off of this, we're going to also have a partial, or pardon me, not partial, just dx nu divided by d tau. So putting this all together, what do we have? Well, we know that this has to be equal to 0. We said that at the beginning because from Tom's point of view, the ball just isn't moving. It's not accelerating. So putting this equation all together, what do we have? Well, we have the following. This right here is the equation we are left with. We can do a couple things to simplify it. We can multiply both sides by partial x lambda, where lambda is just a number, with respect to x alpha. And the reason we can do this, it should be noted, is that we aren't actually summing over either lambda or alpha. They are just numbers. But what do we get when we multiply all of this out right here? Well, you'll see with this first term, we have partial, the alpha component of Tom's coordinate, lambda first, I suppose, so lambda, and then we have this bit right here. And you might recognize this as the Kronecker delta, specifically, Kronecker delta, and then lambda mu. What this is that whenever lambda is equal to mu, then we'll get 1, but if lambda does not equal mu, we'll just end up with 0. So what do we have? So in total, we have Kronecker delta, lambda mu, and then times second derivative of this right here with respect to proper time. So second derivative of my coordinates with respect to proper time, and then plus this mess right here. And that is the messy second half of the equation. But conveniently, we actually do have a simpler way to express this term right here. You may or may not recognize it, but this right here, these are actually just the Christoffel symbols of the second kind. But this right here is just going to be gamma, and then lambda mu nu. So that right there is just our Christoffel symbols, meaning that we can express this equation much more concisely, especially taking into account this right here, that there is actually only going to be non-zero whenever gamma is equal to mu, so we can just rewrite this whole thing. And this right here is what is sometimes referred to as the free fall equation, relating both scenarios with a single equation, whether we are accelerating at the same rate as the ball, or we're at that one just dropping it and observing it like that. Either way, the motion is described with this equation right here, no matter your coordinate system. So considering this is a video about free fall, I think it would be a little bit fun to see if we can somehow get Newton's equations or some of Newton's laws, specifically the one about gravitation, out of this very strange one right here. In the Newtonian limit, we have speeds that are not close to the speed of light. So what exactly does that mean right here? Well, you'll see that we have derivatives here of velocities with respect to proper time, or the derivatives of our position with respect to proper time. So if we were to rearrange this, we see that, just take this first one right here, right? We have dx mu with respect to proper time. So if we multiply the top and bottom by d over dt, what we actually find, d over dt, we can just swap these two in the denominator. So what we end up with is just going to be dt and then d tau. This right here is just going to be our Lorentz factor, And since we are dealing with non-relativistic speeds, we can just assume this to be 1. So now we're dealing with just this term right here, this d over dt times our coordinates. And again, in the relativistic limit, we're assuming that we aren't really close to the speed of light. So in the scheme of things, we have this for mu equaling 1, 2, or 3, so not our time component. This right here is going to approximately equal 0, because we aren't moving that fast. But for our first component, right, so that for mu equals 0, we're just going to have, well, dt over dt, because time we're going to consider our first component, and that's just going to be 1. So what exactly does that tell us? Well, it means that the only time we get a non-trivial solution to this equation is when mu equals nu and equals 0, right? So we can throw that all into this equation above, and we can get the following. We have still a d squared x lambda, and then d tau squared. And then we're going to have plus, well, these two terms right here we just discussed were 1. So then we have just our Christoffel symbols, gamma lambda, gamma lambda 0, 0, and then equals 0. But what exactly, let's really focus in on this term, what exactly is gamma lambda 0, 0? Well, the definition of our Christoffel symbols, using a different definition of them, we have 1/2 and then times our metric. But since the bottom two indices are 0, we're just going to have, well, gamma and then, I don't know, some beta that we're going to sum over, right? And then in our parentheses, we have the partial derivative of 0th component of our metric, and then with respect to, well, our 0th component, which is just going to be time. And that's going to actually be the same one. That's our next term. So we can just add a 2 here. And then minus the partial derivative of our metric, minus the 0, 0th component of our metric with respect to our beta right here, which we are summing over. But since this is the Newtonian limit, and also just to keep things simpler and to not get out of hand, what we can do is approximate our metric as the following. We can say that that g mu nu, it can be approximated as the following, just our Minkowski metric right here, so mu nu, and then plus some perturbation of that, so we'll denote that using h right here. And if we approximate this as the following, so this is going to be a static or semi-static field, then this term right here is just going to be 0, because we're assuming that it's static, or at least semi-static, so that right there can be approximated to 0, which gives us, well, the following. 1/2 and then times g lambda beta, throw the negative out front, and then times the partial derivative of g0, 0 with respect to x beta. And one way we can simplify this is by recognizing that we have this partial derivative right here, which can just be represented by a partial symbol and then a beta right there, but then you'll see that we also have this metric right here. So we can just raise the index of this right here, and we can simplify this term to -1/2 times partial beta up in the upstairs, and then times g0, 0. But considering we're differentiating this, we only have to consider this h part right here because, well, this right here is not changing. That's just 1. If we differentiate it, it's just going to be 0. So we're just going to have h0, 0 right here. So what do we have in total now? We have d squared x lambda, or I do apologize, this should be a lambda. The second derivative of x lambda with respect to proper time is equal to -1/2 this right here. And you'll see here one more thing, that because, as we discussed earlier, the derivative of this metric with respect to time, since it is static, since we're assuming it's not changing, the derivative of that is just going to be 0. So if we have, so it's this right here, if we have the derivative of our metric with respect to time, that's just going to be 0. So really, this right here is just going to be the gradient, because the 0th component of it it's just going to be, well, a derivative with respect to time. And because the derivative of this h00 term right here with respect to time, again, because we're assuming it's a static or semi-static field, it's just going to be 0. So what we can say is that partial 0 of h00, this right here is just going to approximately be equal to 0. So with this, and because gamma can only be 1, 2, or 3, and not 0, we can express this as just the regular gradient operator. So we can just say that this right here is actually just, in fact, negative 1/2, and then nabla, or upside down triangle, h00. And you'll see here that this actually does closely resemble Newtonian gravity. And you might say, hold on, that sounds, sounds a little bit absurd, but seriously, it's not too far off, because this right here is a second derivative of a position with respect to time, or proper time in this case, but time nonetheless. What we have is an acceleration of some sort, and on this right side we have the gradient of some potential. So to really draw a parallel, here is Newtonian gravity. We have, well, the force of gravity, g of r, is going to be equal to just, gm over r squared. But if we want to put that in in terms of some sort of potential, we can say that this is going to be, well, just nabla negative gm over r. So seeing these two, there are a lot of similarities between them, and to a certain degree we have shown that this equation does in fact give us something to do with free fall, and it's not just nonsense. One more nifty thing you can actually do with this equation is change these derivatives with respect to time right here. You can actually change those, and you can prove this more rigorously. There's a nice wiki page I found that actually details this nicely. But you can actually change this from being with respect to time to other variables, right? So, for example, if we were to change this d tau from proper time to, say, distance or arc length, if we change this to ds, what this will actually give us is the shape of a geodesic. Specifically, if we have some shape, what's the fastest, not necessarily fastest, but what's the shortest distance between 2 points? So, just for funsies, say we have a plane, right? Literally just a square plane, a Euclidean plane. Doesn't matter how many dimensions we're in. And let's find the shortest path between 2 points in this Euclidean plane, which we would assume is a straight line. Let's prove it, shall we? Because this is just flat space, we're not going to have any curvature. And we know that our Christoffel symbols right here deal with second derivatives and the curvature of our space. But because there is no curvature, all of our Christoffel symbols are just going to be 0. So this whole term is just 0. So what are we left with? Well, we're actually left with, well, d squared x lambda, and then ds squared equals 0. But this is actually a pretty easy equation to solve. We can just integrate twice, really. And from that, we find that x lambda, so our lambda-ith component of our curve right here, is going to be equal to, well, just some a times, well, for lack of a better letter, I'll just use s, as, and then plus b. And what is that the equation of? That's the equation of a line. So in a Euclidean plane, in however many dimensions, the shortest distance between 2 points is indeed a straight line. So I hope you all enjoyed this video. A little bit different, but I really enjoyed making it. So I hope you all have a great start to the holiday season, and I will hopefully see you all in the next video. Thank you for watching.